sklearn, Linear Model, Logistic Regression. A deep dive. What is logistic regression? Logistic regression is a powerful statistical model used for binary classification problems. It predicts the probability of an event happening based on a set of independent variables. Unlike linear regression, which predicts a continuous output, logistic regression predicts a discrete output, typically 0 or 1, representing the likelihood of belonging to one of two classes. The math behind it. The core of logistic regression lies in the sigmoid function, also known as the logistic function. This function takes a linear combination of the input variables and transforms it into a value between 0 and 1. This value represents the probability of the event occurring. Key concepts. Linear combination. The model calculates a weighted sum of the input features. Similar to linear regression, these weights are learned during training. Sigmoid function. This function squashes the linear combination into a probability range between 0 and 1. Decision boundary. The model uses a threshold, typically 0.5, to classify instances. If the probability is above the threshold, it's classified as 1, otherwise as 0. Advantages of logistic regression. Simplicity and interpretability. Logistic regression is relatively simple to understand and interpret. The coefficients associated with each feature provide insights into their influence on the outcome. Efficient training. The model can be trained efficiently even on large datasets. Robustness. It can handle multicollinearity, correlation between independent variables to some extent. Regularization. The model supports regularization techniques like L1 and L2 penalties, which help prevent overfitting and improve model generalization. Disadvantages of logistic regression. Linear decision boundary. The model assumes a linear relationship between the features and pay outcome. It may not perform well with complex, nonlinear relationships. Sensitivity to outliers. Outliers can significantly influence the model's performance. Limited feature interactions. The model does not directly handle interactions between features. Key parameters in sklearn. Linear model, logistic regression. YAML structure explanation. YAML. Penalty. L2 regularization type. L1. L2. Elastic net. Or none. Dual false. Dual or primal formulation. True for larger datasets with many features. TOL 0.0001 tolerance for stopping criteria. C 1.0 inverse of regularization strength. Smaller values enforce stronger regularization. Fit intercept. True whether to calculate the intercept term. Intercept scaling. 1 scaling for the intercept term. Class weight. None. Weights associated with classes can be balanced for imbalanced datasets. Random state. None. Seed for random number generator. Solver. LBFGS algorithm to use in optimization. LBFGS. Newton CG. Liblinear. SAG. Saga. Maxiter 100 maximum number of iterations for optimization. Multiclass auto strategy for multiclass classification. OVR. Multinomial or auto. Verbose 0 verbosity level. Warm start. False whether to use previous solution as a starting point. N jobs. None number of jobs to run in parallel. L1 ratio. None ratio of L1 regularization to total regularization for elastic net. Detailed explanation. Penalty. This parameter controls the type of regularization used. L1 regularization adds a penalty proportional to the absolute value of the coefficients, leading to sparse solutions. Many coefficients become 0. L2 regularization adds a penalty proportional to the square of the coefficients, leading to solutions with smaller coefficients. Elastic net combines L1 and L2 penalties, providing a balance between sparsity and shrinkage. None. No regularization is applied. Dual. This parameter determines whether to use the dual or primal formulation of the optimization. Problem. True. Use the dual formulation. Often more efficient for datasets with many features. False. Use the primal formulation. Often more efficient for datasets with fewer features. Toll. This parameter sets the tolerance for the stopping criteria of the optimization algorithm. It defines the level of precision required for convergence. C. This parameter controls the inverse of regularization strength. Smaller values, e.g., 0.1, stronger regularization, leading to smaller coefficients and potentially more sparse solutions. Larger values, e.g., 10, weaker regularization, allowing larger coefficients and potentially a model more prone to overfitting. Fit intercept. This parameter determines whether to calculate the intercept term in the linear model. True. Calculate the intercept. False. Do not calculate the intercept. Intercept scaling. This parameter scales the intercept term. Class weight. This parameter allows you to assign weights to different classes. This is useful when dealing with imbalanced datasets, where one class has significantly more samples than the other. None. All classes are given equal weight. Balanced weights are automatically assigned inversely proportional to the class frequencies. Random state. This parameter sets the seed for the random number generator. Use it to ensure reproducible results. Solver. This parameter specifies the optimization algorithm used for training. LBFGS, a quasi-Newton method. Generally efficient for medium-sized datasets. Newton CG, another quasi-Newton method. Often faster than LBFGS but may require more memory. LibLinear, a linear solver. Suitable for large datasets or datasets with many features. SAG, stochastic average gradient descent. Efficient for large datasets. Saga, a variant of SAG, which is robust to outliers. Maxiter. This parameter sets the maximum number of iterations for the optimization algorithm. Multiclass. This parameter specifies the strategy for multi-class classification when you have more than two classes. OVR1 vs REST strategy. A separate binary classifier is trained for each class against all others. Multinomial trains a single classifier for all classes simultaneously. Auto chooses the best strategy based on the dataset. Verbose. This parameter sets the level of verbosity during training. WarmStart. This parameter allows you to use the solution from a previous training run as a starting point for the current training. NJobs. This parameter specifies the number of CPU cores to use for parallel processing. None. Use all available cores. -1. Use all available cores except 1. N. Use n cores. L1 ratio. This parameter is only used with the elastic net penalty. It controls the ratio of L1 regularization to total regularization. Using logistic regression in Python. Python. From sklearn, linear model import logistic regression. From sklearn, datasets import load iris. From sklearn, model selection import train test split. Load the iris dataset. Iris load iris. X iris. Data. Y iris. Target. Split the data into training and testing sets. X train. X test. Y train. Y test train test split X. Y. Test size 0.2. Random state 42. Create a logistic regression model. Model logistic regression penaltal 2. C 1.0. Random state 42. Train the model. Model. Fit X train. Y train. Make predictions on the test set. YPRED model. Predict X test. Evaluate the model's performance. From sklearn, metrics import accuracy score. Accuracy score test. YPRED. Print accuracy. Accuracy. Key takeaways. Logistic regression is a versatile and powerful algorithm for binary classification. Understanding the parameters and choosing appropriate values is crucial for optimal performance. Regularization techniques are essential for preventing overfitting. The model's performance can be influenced by factors like data quality, feature selection, and hyperparameter tuning. I hope this detailed explanation provides a comprehensive understanding of sklearn, linear model, logistic regression and helps you effectively use this algorithm for your classification tasks.